Hi, everyone. Welcome to the Monday seminar. Really nice to see you all. We were off last week because of the earthquake workshop that was in Carjaz, and we're off next week with another little holiday. But we're very fortunate to have Agathe Eijsink with us this week, talking about some work that she's been doing recently at Penn State. Her background you read all about. Maybe I'll say one thing, and that is she got her PhD with Madhukari in Bremen, and she's been in the U.S. In the Penn State lab for a couple of years now. So she is happy to be interrupted with points of clarification. You want to say, I don't know, some minor point along the way to make it a little bit more interactive. But we'll have plenty of time at the end for questions and discussion. So major points, let's keep them to the end. Otherwise, we just invite you to mute yourself right now and do what you want with your camera. And then if you have a point of clarification, just go ahead and unmute. But thank you very much, Agathe, for being here. I'll turn things over to you.
Yeah, well, thanks, Chris, for the invite, and thank you all for tuning in today and listening to what I have to say. So as Chris said, this is some of the recent work I've done at Penn State, and it's sort of grouped together by relating frictional behavior to contact area and the changes that occur on the contact. And all of this work has some sort of relevance for geothermal reservoirs, because the project that I work on is called the Utah Forge project, which is a geothermal project that I will explain a bit more about in a minute. I have to thank some people here. So the people that have helped me with all the work I've done here are Derek Ellsworth, Chris Marone, Jacques Riviere, and Parisa Shukui, who are all PIs and co-PIs on the project. And then Clay Wood and Raphael are a former and a current grad student here that have helped me with some of these experiments I'll show in a minute. So first of all, okay, why do we think contact area and frictional behavior should be related? And that all comes back to like basic friction theory, where we think that like fault surfaces are not exactly smooth, they're rough, and they have asperities on one side of the fault that are pushing into the other side of the fault. And those contact asperities deform the other side of the surface. So how that, like the hardness of the material as well as the yield strength of the other side really determine how far that asperity indents the other side and how much material it has to move there to slide, which is why frictional behavior and contact area in theory should be related. Contact area is a bit difficult to image, so it's not always a really easy relationship to study. So the two studies I'll be showing here is studying healing rate. And healing rate on the one hand influences contact area, and on the other hand, we can study how it influences frictional behavior. And then the other thing is fault surface roughness, and that changes with displacement on the fault surface. And I also studied how that, like on the one hand, changes the contact area, and on the other hand, frictional behavior. So first, a little bit about the Utah Forge project, which of course is in Utah here, that white dot right there. It is it's short for the Frontier Observatory for Research in Geothermal Energy, and it's really a demonstration project for enhanced geothermal systems. So it's not meant to be like producing electricity at any point in time. But the idea behind it is that wherever you have heat, as long as you get a fluid to transport that heat, you can build a geothermal system pretty much anywhere. But you need permeability in the rocks to actually transport the fluid. So the enhanced part about enhanced geothermal systems is really about enhancing the permeability to make it viable for like electricity generation. The bottom hole temperatures at this site are around 200 degrees Celsius. So that's sort of the temperature range that we work with. And then there's two main rock types at this location. One is a granitoid and one is a gneiss. So these images are about 4 centimeters wide and 6 centimeters tall, and these are the actual samples that I work with. The granitoid in composition is fairly similar as westerly granite, except it has a bit larger grain size. And the gneiss has a bit more biotite in it, about 20–30%. And it has some really coarse grains. So you see some of these coarse grains, they range up to like a centimeter in size. So then diving right into the first topic I'm going to talk about, and how healing rate influences frictional behavior and contact area. So we know that healing behavior is time dependent, and important for geothermal reservoirs is that it influences the permeability as well as the frictional behavior. Because in geothermal reservoirs, you always have the trade-off between you want to keep the permeability high, but you don't want induced seismicity. And then also important, we know that healing rate is very dependent on the presence of fluids. And geothermal reservoirs always have water or some fluid present. And then it also increases with temperature. So this is just quickly, like, I guess a lot of people know here how we study a healing behavior, but we commonly use slide hold slide experiments, where we slide at a constant rate, then we stop sliding for a certain amount of time, and then we reload the fault, and we get the peak in friction behavior. So we compare from a steady state friction level, we compare how much the peak friction is increased after holding at a certain amount of time. And then we plot that delta mu, and we plot that for different hold times, and we get, I'm going to assume this is a linear increase over time. Although there is like some debate about it, whether it's actually linear or not. But for this talk, I'll just assume it's linear. And we fit a linear line through those points, and we call it the healing rate beta. And then we know that this is temperature dependent. There's people that have studied the temperature dependence of these kind of materials. And it mostly, the healing rate increases at temperatures above 200 degrees Celsius. But most of these studies don't have water present on the surface. And then other studies that do test whether water makes a big difference or not really show that the presence of fluid has a huge impact on the healing rate. And then the other thing about studying contact area is that contact area is actually not a very straightforward thing to measure. So this is the work by Dieter and Kilgore that I'm sure many of you know, but it's like when you hold a fault stationary for a certain amount of time, like after 1 second, you get this red area, and then that area grows with time. The yellow rims are after 100 seconds, and then the blue rims that might be a bit difficult to see for you are after 10,000 seconds. But this is studying like contact area on a plexiglass plate, and like we study rock surfaces, so you can't actually see inside there. So what we can do is that we use P waves. So we shoot from a PZT on one side of the sample. We shoot a P wave through the sample, and the P wave starts off as a very controlled half sinusoid, and then it interacts with the fault surface, and then we measure some kind of complex shape of that wave on the other side. And that is supposed to be sort of a proxy for contact area. So this is the actual setup that I use. So like I said, it's our slide hold slide experiments. For this, I only used a nice sample, which is the deeper of the two. That's what the actual sample looks like. It's a 3-inch long core, 1-inch diameter. It has a 30-degree single inclined fracture pre-cut through it. And then on both sides are these steel tubes that sit inside, like embedded into the side, that provide fluid to the fault surface. So there's one here, and there's another one in the back there on the opposite side. That sample is jacketed in a combination of some rubber jacket and a Viton jacket, with the Viton being temperature resistant. And then that assembly goes into this triaxial cell, where we have heater tape on the outside to heat the assembly. And we actually measure the temperature on the inside. So we assume that everything inside that sample holder is heated. And we can't really control the temperature that we reach the temperature that we want. But after the temperature has stabilized at a certain point, it is like constant within 1 degree Celsius for the remainder of the experiment. So that's just a schematic setup of the setup here. And there are PZTs are embedded in the steel end caps that we use that sit like directly behind the fault surface or the sample on both sides. So then diving in some of the results. So this is a temperature legend that I'll use for the remainder of this section. So warmer colors are warmer experiments when you reach up to 165 Celsius. And this is just plotting the friction coefficient. So what you see here, where it like decreases a bit, is where the sample is held stationary. And then when you see a peak, that's the reactivation. And what you might see is that this data looks kind of noisy, which has two reasons. The one is that we have fairly low temporal resolution in this setup. So our maximum sampling rate is about 7 Hertz. And the other reason is that the noise actually has that inherent heterogeneity. So more homogeneous samples, we get much cleaner curves, but the noise is a bit difficult to work with. So for holds, I can only really get decent peak friction values for hold times longer than 10 seconds. But to account for that, I do go to fairly long hold times, up to 10,000 seconds, so that I still get like a decent curve, like enough data points to actually fit a curve. So what you might see initially is that like the warm experiments have lower friction coefficient than the cooler experiments, although it's not a really clear relationship. It does seem there's like a decrease in steady state friction with temperature. So that's interesting because it starts off at like the 0.6-ish values that you would expect for a granite or a gneiss, but it decreases to about 0.4, which is a fairly dramatic decrease with temperature, especially as this is not like really high temperatures. And then looking at the healing behavior. So this is just one example of the room temperature experiment where we hold the sample stationary for 3,000 seconds. We get this decrease in friction coefficient, and then the peak when we increase again, and we measure the increase from the steady state friction from before. When you plot all those data points and we just fit a linear line through it, we get some kind of healing rate beta. So this is the data from all the different temperature experiments. And even though data is a bit noisy, it is very obvious that at higher temperatures, we get increased healing. And if you plot the healing rates over temperature, that is an increase from about 0.005 to about 0.02. So 4 times higher healing rates at temperatures in the 150 centigrade range compared to room temperatures. And then there was something that we did not expect at all. When we did the experiments at higher temperatures, we saw an increase in friction coefficient during the hold. So the black here is what you would sort of expect, a decrease in friction coefficient all the time when you're holding the sample stationary. But with increased temperatures, we see this increase. The orange is quite dramatic here. And after a lot of head scratching, I realized that it's most likely because during this slide, we inject water into this actual volume here that pushes the piston forward. And that temperature is the water is at room temperature. And as the entire assembly is heated, it's likely that this water in the actual piston gets heated and drives that piston forward during the actual hold. Because a hold is really that we like stop the pump and it's not driving any fluid forward, but the pump is like slightly far away from the actual reservoir. So as the water in that actual reservoir expands, it just pushes the sample at a very slow rate, and that increases the friction coefficient. So even though that's not at all what we wanted, I decided to take advantage of it, because that allows us to like model the slide-out slides as velocity step experiments. Now I do have to make some quite rigorous assumptions here, but I think they're valid, and I can explain to you in a bit more detail if you want later on why I think those assumptions are valid. But I modeled all the down steps, assuming they reach a sliding velocity of 15 nanometers per second, which is sort of what we observe for the warmer experiments. And then, as you might see from this curve, that increase in friction coefficient it takes about 100 seconds or 1,000 seconds. So I modeled all the 1,000 seconds holds. And as you can see here, I got decent fits. So that's encouraging. And showing that data, I can see that A minus B decreases a fair bit with temperature. And that is really an increase of B with temperature. Whereas A decreases slightly, but these scales are quite different. And it's really the increase in B that causes this dramatic decrease in A minus B. And it's quite interesting that we get this switch over from velocity strengthening behavior at low temperature to velocity weakening behavior at temperatures over about 70 Celsius. Now, rate state friction parameter B has been related to a change in contact area. And you can sort of see it as like a change in friction coefficient with a natural logarithm of hold time. Whereas beta is really defined as a change in friction coefficient over the base 10 log of hold time. So that means they should be related with just that constant factor that accounts for the difference between natural log and 10 base log. And when I plot them, they actually overlap quite nicely. So that does suggest that we can relate B and beta. So both rate state friction B and healing rate beta have been related to an increase in contact area with time. And the temperature dependence that we see in both beta and rate state friction B suggests that contact area would increase faster at higher temperature. And that's not completely unexpected because a lot of studies that look at the actual deformation mechanism have pressure solution-based mechanisms as the reason for the increase in healing rate. And that also explains why the presence of fluids is so important. So then we measure the P-wave velocity as well as the amplitude of the P-wave. And this is just to zoom in at the timing of how these change. So this is an overview of a part of an experiment. This is one of the holds where you can see that increase in friction again. And then in here is a slide that's very short compared to the holds because the holds are so long. So if you look at the RMS amplitude of the P-wave in green here, you see during a hold, RMS amplitude increases and P-wave velocity increases as well in red here. And then in black at the bottom here, I have the acoustic emission rate, which we also measure during the entire experiment. We monitor for acoustics emissions that are generated on the sliding surface. So this panel in the middle here is zoomed in one of the slides. And when we look at the timing of things, when we start sliding, you see friction coefficient increases. And during that time, RMS amplitude as well as P-wave velocity start decreasing already. And there's pretty much no acoustic emissions yet at that time. Then once the sample starts to really slip, you see that spike in slip rate here is when like the peak friction decreases and it goes towards a sort of steady state. We see both P-wave amplitude and velocity have like that big drop in amplitude and P-wave velocity, which is likely related to just like an opening of the surface and a loss of contact area. And then the RMS amplitude levels off and is sort of constant for the remainder of the slide, whereas P-wave velocity keeps on decreasing. The acoustic emission rate really spikes upon like the when we see the decrease in friction with the same like spike that we see in sliding velocity. And after that, it's fairly constant during the remainder of the slide. And then as soon as we stop and we start the next hold, acoustic emission rate decreases very rapidly. And then we don't really see many acoustic emissions for the remainder of the hold. Interestingly enough, I already mentioned that the samples get velocity weakening with higher temperature. And at 120 degrees Celsius, we actually had some spontaneous slip events occur during the hold. So that's what's happening here. This entire period is a hold. where we don't drive the piston like actively, you see that increase in friction coefficient in the beginning again. But after that, most of the holes look like with a constant friction coefficient. And then here, as well as at the end here, we have 2 spontaneous slip events, which is interesting because then we can also see how P wave velocity and amplitude behave during spontaneous slip events. So it's really just like the drop in friction coefficient, and this drop in friction coefficient about 0.02. We are at a normal stress of about 10 MPa, so that's really like a 200 kPa stress drop. So they are fairly sizable. Interestingly enough, the P wave amplitude already starts to decrease. So it was increasing all the time here, but it starts to decrease already minutes, like 2-3 minutes before the actual slip event. Whereas P wave velocity does not really show anything except for this little blip when the actual event occurs. But RMS amplitude of the P wave really shows this big decrease when the slip event occurs, and it's then sort of reset to a lower level and starts increasing again. Acoustic emission rate also picks up slightly before the spontaneous slip event, but that's only like a matter of seconds. So then when we look at the P wave velocity and RMS amplitude for all of the data at all temperatures, so this is just from one hold, a 3000 second hold, but for the different experiments, we see that P wave velocity increases for all experiments, but it doesn't really show a temperature dependence. So it increases for all experiments pretty much the same. And it doesn't increase that much, relatively speaking. It's only like, it's not even a full percent. RMS amplitude, on the other hand, shows a big temperature dependence, where the colder experiments have a much smaller increase, and the warmer experiments show a very big increase in RMS amplitude. And these changes are also like much, much bigger than the changes in P wave velocity. So then we start sort of thinking about, okay, what does that actually mean? So P wave velocity increases with time, but it's not faster at higher temperatures. Whereas we said that like contact area increases at higher temperatures. That's how we explain the increase in frictional healing rate and the increase in rate of friction parameter B. So that means P wave velocity is not really sensitive to contact area, maybe. P wave amplitude, however, does increase with time, and it increases faster at higher temperatures. So that seems to track the contact area of a surface. Although there is like a couple of explanations of why we actually see a change in RMS amplitude. And as I said, we can't really measure contact area, but we can measure some related properties, or at least we can model state. So when we do model state, we of course have to assume a state evolution law. And then I plotted here for the curves for true holds in orange, and for the down steps that I modeled with the 50 nanometer per second sliding rate in blue here. And we see that the shape of the RMS amplitude curves sort of fit, well, they best fit with the slip law for a true hold. Although the state increases, like it almost doubles. And we see like a 10-20% increase for most of the holds here. So it's not a perfect fit, but at least like the shape sort of fits. The other thing though is that if we say, okay, with higher temperatures, the main thing that changes is the B value. When we increase the B value, if you model the state actually increases less, whereas we see RMS amplitude increases more for higher temperatures. So it doesn't really work, but sort of, maybe. The other thing is stiffness. And stiffness we can of course measure from the reloading. So instead of like taking this like delta mu from the steady state friction to the peak. I take the increase in friction from the end of hole friction to the peak, and then the displacement over which that happens, and I call that stiffness, reactivation stiffness. And these points in black here are from the room temperature experiment, and you see it increases for longer hold times. And RMS amplitude also increases for longer hold times, and both of them are, I think, not quite linear, but they sort of follow the same shape. But again, this works for one experiment. And then when we do experiments at higher temperatures, stiffness actually decreases with temperature, whereas the RMS amplitude change increases with temperature. So stiffness also doesn't really describe this increase in RMS amplitude. So we don't really know how to measure that contact area. State, stiffness, and contact area are also sort of related. I mean, state, we don't actually know what it means, but a lot of the ideas go towards the direction that it represents the contact area. And stiffness would also, of course, depend on contact area, because higher contact areas make more rigid fault surface, so that would increase the stiffness. So maybe it's just a combination of all the effects. So coming to a close on this part of the talk, we really see that frictional healing increases with temperature when water is present, and it even increases a fair bit at these low temperatures, which are relevant for geothermal reservoirs. And then P-wave velocity is not temperature dependent, but P-wave amplitude is temperature dependent. So we think P-wave amplitude is a better indicator of a change in contact area. So then I'll move on to the second part of my talk, where I talk about a different set of experiments where we use roughness and changes in the roughness to relate contact area to frictional behavior. And we know from different experiments that RMS roughness affects permeability. This is a map of transmissivity, which is sort of a proxy for permeability. And with different roughnesses, permeability changes. We also know that different roughnesses change the friction behavior. And then this is a map of different values for stability, so A minus B values, for different RMS roughnesses and normal stresses. But I want to explain a little bit what RMS roughness is and what it cannot do. So we know that roughness is an important factor to measure, and it influences frictional behavior and permeability. So this is from a paper that really studies tribology. So it's probably nothing that you have seen before, but it does a nice job of explaining what RMS roughness is. And I'll focus on this top right figure here first, and the top left here. So I think if many of us, if you would look at these two roughness profiles, you would call this left one rougher than this right one. But RMS roughness describes a deviation from the mean roughness. So in this left figure, the mean roughness would sit right in the middle there. So all of the points fall fairly close to the mean roughness. So this has a lower RMS roughness coefficient, whereas here the mean roughness would sit slightly below the surface, and then all of a sudden almost all the points deviate from the mean. So even though, at least I would call this surface smoother, it has a higher RMS roughness coefficient. And then this top right and this bottom left actually have the same RMS roughness value. But if you would model the contact area of these two surfaces, this surface would probably have much larger contact asperities. So RMS roughness is in itself is a measurement that's used a lot, but it doesn't really describe it doesn't capture all the behavior of a surface. And during experiments, when people compare roughness, RMS roughness is often the most used one. And we describe gridded surfaces that look like this. And then a rougher surface would be using a rougher grid size. But during slip, a fault surface actually changes. and it changes and it becomes like smoother and looking like this. And then if you would ask like a structural geologist to describe a perfect fault surface, it would probably look something like this, which is much more like the roughness profiles that we get at the end of experiments. And the roughness that we start off with does not look like a natural fault surface at all. And then in terms of like permeability, a change in roughness like this has a huge impact, because permeability, water doesn't flow on the entire surface, but it really channelizes in like preferred flow paths. So striations like this can really channelize fluid flow. So even though these surfaces have fairly similar RMS roughness values, it makes a huge difference for permeability. So why this would be relevant for geothermal reservoirs is because if you make new fractures, they start off as fairly rough and isotropic. Whereas if you think about reactivating already pre-existing faults, as well as slipping on new fractures, that would smoothen fractures, and those faults might be like smoother and isotropic. So for this, I used both of these granitoid and gneiss samples. And then what I did is I ran a series of experiments on both of these samples. And I measured the roughness before the experiment and then after each experiment. That's what the surface looks like. So it has a tall side and a shorter side, and the tall side moves down so that the contact area is constant during the experiment. And then I make scans of the entire length of the surface and the maximum width that the device allows me to measure, as well as higher resolution areas at the top, middle, and bottom of the surface that are about 4 by 4 millimeters in size, which sort of fits with the size of the PZTs that are embedded in these blocks. And then I do velocity step experiments with these samples, and we have fluid flow in the direction of shear. So this is just like a schematic of the actual block. There's PZTs that sit right behind the surface. There's 3 on the short side and 4 on the tall side. And then fluid ports supply water to the bottom that's distributed along the edge of the fault, as well as like another fluid port towards the top of the sample. And we have a fluid gradient. We flow from the bottom to the top. There's a 1 MPa fluid gradient so that we can measure the permeability throughout the entire experiment. Those blocks sit in the pressure vessel of the BIAX here at Penn State. That's what the actual setup looks like. So the sample is in the orangey jacket here. And then we have internal displacement sensors that measure the horizontal as well as the vertical displacement. So these are images of the samples. This is the granitoid. And you might think this roughness does not change very much, but it does. So all of the tops become a lot smoother, whereas the valleys sort of stay the same. So it's really like shearing off those peaks, sort of as this example that I explained with the RMS roughness. Sliding directions from top to bottom here. So if I show the measurements, you can see the RMS roughness does not actually change very much. RMS roughness is a lot higher for the top of the sample here because there's some pre-existing fractures. And this measurement area is just like intersecting with one of those pre-existing fractures. So that's why the RMS roughness is so much higher here. But overall, RMS roughness is fairly constant throughout the experiments. And then I use this other parameter called the peakedness of a surface. It's not a very commonly used parameter, so I'll just take a moment to explain what it is. And it is the average curvature of peaks. So it's sort of, I use it as sort of the inverse of the radius of a contact asperity, because because that's what you would think is actually in contact with the other surface. So an decreasing peakness here would mean rounder peaks, and I interpret that as an increase in contact asperity size. So then the gneiss. This change is a lot more obvious. So the gneiss really becomes striated. But again, if we look at the measurements, RMS roughness is a bit more variable here. But again, it doesn't really change a whole lot. And then the peakness, again, it decreases. And I think this is actually quite interesting because it decreases a lot more for the top than the middle and the bottom. I do see a lot more, I also visually see a lot more changes at the top of the sample than the bottom, which I think might have to do with that pore fluid gradient, because the top of the sample experiences a 1 MPa higher effective normal stress. So that might just like change the roughness more. So overall, like this shows the same development as the granitoid. Comparing the two samples, the granitoid has a lower RMS roughness of about 10 micrometer. The gneiss has slightly higher RMS roughness of about 20 micrometer. So those are the values that I assume as aperture for the permeability, because to measure permeability, you have to assume a certain aperture where the water would flow through. And then comparing the peakness, the granitoid actually has lower peakness, so larger asperity sizes than the gneiss, although both of them decrease like after the first experiment. So then the friction data. As I mentioned, I ran velocity step experiments. This is data from the 5 experiments that I ran. So in black and gray is the gneiss, and in green is the granitoid. Black is the first experiment, and then lighter colors are subsequent experiments. And I've numbered them, and the first experiment is experiment 1. And then I ran 2 times the same velocity step sequence, which are 1A and 1B. And the velocity step sequence starts with a run-in at 10 micrometers per second, and then 1, 3, 10, 30, 100, 300 micrometers per second. Sample is unloaded or slightly unloaded, and then that sequence is repeated a second time. Except for the granitoid, the third experiment, the first sequence was aborted halfway due to like an experiment failure. So that's like first a half experiment, a velocity step sequence, and then 2 more full experiment sequences. So looking at the steady state friction coefficient and how that changes over experiments, I plotted data from the 10 micrometer per second. So during the run-in at 10 micrometer per second, and then during the velocity step at 10 micrometer per second. And the gneiss are the circles here. And you see that overall there's a decrease in friction coefficient. And the granitoid also shows that same decrease in friction coefficient, but it already starts off lower at about values of 0.6, whereas the gneiss is about 0.7. And relating that to the contact asperity shows actually something I find quite interesting. So when I say okay, contact asperity is from the peakness that I measure, and taking, because I did the measurements before the experiment, I take the friction coefficient from the initial run-in, so from the first run-in. When I plot that, I see a correlation between contact asperity radius and friction coefficient, with smaller contact asperities showing higher friction coefficient, which I interpret as smaller contact asperities means that like more normal stress concentration on those asperities, and they may sort of plow deeper into the other side, and that way you have to they need more force to displace, so that would result in a higher friction coefficient. Looking at the permeability data, so same color coding as above. The green is the granitoid, the black and gray are the gneiss. You see a big velocity dependence of permeability. So on the left here, I again have like data from the 10 micrometer per second velocity steps and the run-in. And then you see that permeability, it sort of increases for both the granitoid and the gneiss, but it really doesn't change very much. This is in the same order of magnitude. and permeability can really vary orders of magnitude. And the velocity dependent effect has orders of magnitude change. So the open symbols here are at 300 microns per second, and that has a much bigger effect than the overall roughness change, which maybe is not so surprising because permeability has been linked to RMS roughness. And we saw that the RMS roughness does not really vary much for these experiments. So this is like just a plot from Agathe et al. That shows like RMS roughness really has like orders of magnitude changes in permeability, whereas like for my data, the permeability is like really fairly constant. So then going into the frictional stability parameter, A minus B, which is velocity dependent as well. So this is plotted over upstep velocity. And I'll start on the right here with the gneiss. And in this case, so black is the first experiment, and then the colors go towards green and orangey colors for subsequent experiments. So the gneiss is velocity weakening only for the very first few data points. And then with ongoing displacement, lighter colors, it gets more velocity strengthening, higher A minus B values. The granitoid is overall velocity weakening. And it does seem that with ongoing displacement, A minus B decreases. But if I look at the data more carefully, there is actually something quite interesting going on, where during experiments, you're going from the black to the dark blue, for example, A minus B increases. And then between experiments, A minus B decreases again. And I think that has to do with the development of some fines on the surface, a little bit of fault gouge. Raphael actually did some experiments on the gouge itself of this material and its velocity strengthening. And I do see some development of gouge after I open the surface, but I have to clean it off before I do the roughness measurements. So between experiments, the fines that I clear off might explain why then the A minus B decreases again. So the roughness effect would cause a decrease in A minus B, but during experiments, the development of some fault gouge would increase A minus B, is my interpretation at least. Now looking at DC, for the gneiss, DC increases. So lighter colors go up. For the granitoid, it's a bit more complex again, because for the granitoid, especially during later experiments, I quite often need a second state variable to get good model fit to the data. But if I just focus on DC1, it decreases quite a lot from values around like tens of micrometer at first to like really small values. And I think that has to do with the development of gouge as well. So critical slip distance DC has been related to like the size of contact asperities and how much displacement you need to renew asperities. Because the gneiss becomes striated, as contact asperities would elongate and become longer. So increasing DC values would make sense in that case, because you would need more displacement to renew your asperity. Whereas in the granitoid, I think the development of gouge might explain why DCs get so small. Because at first the DC is more of like the actual contact asperity that you're measuring, whereas later on you might get the effect of like the grain size of very fine gouge that controls DC. Then the velocity dependence of permeability. So these permeability values are normalized to the permeability at 10 micrometers per second from the run-in. But because you have that large velocity dependence of permeability, the values around 10 would all plot like around 1. And then at higher slip velocities, permeability increases a lot, which is because permeability actually is with the cubic law is like an increase of width causes a cubed relation result in the permeability. So for the gneiss, we see an effect of like much more permeability increase at higher velocities when the faults get smoother. Whereas for the granitoid, there is again like during experiments, the permeability increases. And then between experiments, when they clear off those fines, permeability in the next experiment is lower again, which would make sense because gouge would like prop open a fault surface and enhance the permeability that way. So I've combined all those observations in a sort of two-end member model where the granitoid is not striated, it's velocity weakening, and it has small DCs. And that's all because those faults become gouge filled. So the development of gouge explains like all of these, all the behavior that we observe. Whereas the gneiss is striated or becomes striated with displacement. It shows velocity strengthening behavior when it gets striated, which to some people might seem surprising, but I've actually seen that before in a paper that's published in 2022. So if you want to see more about why I think that makes sense that velocity strengthening faults are striated, maybe have a look at that paper. And then the increasing DC makes sense with the development of striations and the elongation of asperities. And then the increase in permeability with velocity that we see is because channels are fluid. Fluids are funneled and they flow more directly instead of taking a more tortuous path. And so then it's really important that this is the direction that we measure the permeability in, because if we would measure the permeability in the opposite direction, we might probably have like very different results. So I think that's just a quick summary. I think there is enough time to explain, to go into like the P-wave observations that I have for this data set as well. So as I mentioned, we have 3 transmitters on the short side of the surface and then 4 receivers on the tall side. So that means that we get 12 transmitter receiver pairs in total. And there is a big difference between the transmitter receiver pairs. For example, the more direct pairs have much bigger signals and much better signal to noise ratios. So that's just something to keep in mind when I show the rest of the results, that I have a lot more confidence in the more direct pairs than the ones that go like all the way across. They have like much smaller signals. This is the color legend for my next few slides, and it looks a bit chaotic, I know, but it will make sense. Because I've color-coded them in sort of the direction that the waves go, like the white and the grays are all the most like sort of direct paths, whereas the blues go down this way. And the red and orangey yellow colors are all like the ones that go up. So I've just highlighted 4 of the transmitter receiver pairs here. So this data is all for the granitoid because in this setup, we don't always get all the sensors to work because there's lots of cables and sometimes they just get loose. And for the gneiss, I just don't have so good coverage of all the PZTs for all the experiments. So this data is all from the granitoid. And I mostly just see a big development with displacement. So this is just like some points from the from all 3 experiments, from the beginning, the middle, and the end of each experiment. The sort of chaos that I saw in here can actually be explained quite well if you look at the direction that the different transmitter receiver paths or different receiver pairs take. And if you relate it to the direction of the stressed contacts, because if you apply a shear stress, then the yellow and red colors, they will like go through the stress disparities. Whereas like the white, gray, and the bluish colors, there's no stress in that, like that. The contact disparities are actually sort of opened in that direction. So depending on the friction coefficient, the maximum stress on the sample sort of goes in this direction. And we know that P wave velocity is actually quite dependent on the stress in the bulk. So a lot of the behavior I see in the P wave velocity can actually be explained by the changes in the stress. And then you have to also keep in mind that as I displace this tall side, I also displace the receivers relative to the transmitters. And even though like for the P wave velocity, the calculation, I correct for that like displacement and the change in like length. That means they make a different angle to the maximum stress direction. As well as that when friction coefficient decreases during experiments, that direction of the maximum stress gets more parallel to the normal stress. So I think that's how the decrease in P wave velocity for the stress contact, why that decreases overall, is because that change in the bulk. But P wave amplitude is much more sensitive to changes going on the actual contact. And we see that, except for this first experiment, the stressed contacts have an increase in P wave amplitude that might represent that increase in contact area. Why the other paths parallel to disparities and the most horizontal path, they decrease. Why that is, I'm not entirely sure. I think it might have to do with the gouge formation and that sort of degradation of the actual contact. Then what's also very interesting is if we look at one of the velocity steps. So this top curve here is the friction coefficient during a velocity step from 1 micrometer per second to 3 micrometer per second. And these are all the different transmitter-receiver pairs. And I wasn't exactly sure what to expect, but if we think of how contact area changes during a velocity step, we might expect sort of like an overall decrease in contact area, which would mean that we would expect a decrease in P wave amplitude. And then during the step itself, when you see that increase in friction, and maybe like things just get like pushed together more. So maybe this increase in P wave amplitude during the frictional transient makes sense. So I think maybe this green and yellow, dark yellow, are sort of the behavior that I would expect. But actually there's a lot of variability in the different signals, especially this yellow. I'm not sure if you can see it very well, but this yellow and this red have like pretty much the same shape. And it shows like the opposite, a decrease during the frictional increase, and then an overall increase in P wave amplitude. Same as the black-gray curves, which actually show the smallest signal, even though like those are the directions that most setups measure P wave characteristics in. Is like we always think, oh, we should measure like directly across the fault, but they have the smallest signals. The biggest signals are really in the more oblique paths. So I'm not entirely sure how to explain this. And again, it's sort of like we have to think about what actually like controls a P wave amplitude. Is it the contact area? Is it the state? Is it the stiffness? But how would contact area or state or stiffness, why would it change differently in different areas of the fault surface? It might have to do with heterogeneity of the sample, because the yellow and the red, as well as like the dark gray that show that decrease during the frictional transient, all sort of pass through the same area. So maybe there's just something going on in the sample right here. Or maybe it's because we apply the stress from the top and the top of the sample just behaves different than the bottom of the sample. I'm not entirely sure at this point. So let's get back to some of the points that I do know. And I hope these are sort of the messages that you'll take home from today's talk, from the second part at least. So RMS roughness does not really describe changes in a fault surface, because a change from this surface to this surface makes a big difference for frictional behavior as well as permeability. But RMS roughness does not capture this sort of changes. I saw that friction coefficient correlates with asperity size. And then this striation formation in the gneiss and the gouge formation in the granitoid both increase permeability, and they also both increase A-B or fault stability. P wave velocity and amplitude both depend on the angle with the maximum stress. So that's just some interesting observation. And I think there's a lot more work to do in how to interpret those signals. So that's just a summary from both parts of this talk. And I think I'll leave it at that. Thank you.
Wonderful. Thank you very much. Okay, I will ask people to join me and unmute whatever you want. And thank Agathe for a really great talk. Lots of interesting things to think about. Yeah, and then my recommendation to you is to use the raise hand feature at the bottom of your screen. That'll be the easiest way to put ourselves in an order. It looks like that. I suspect you're all experts at it, but yeah, let's give Agathe just a second to catch her breath, and then yeah, if people have questions or discussion points they want to bring up, please do. And I'm going to stop the recording right now because yeah.